Hey, how's it going there? The goal of this video is twofold. We're going to be talking about inverse functions first of all. And when we're talking about inverse functions, we want to know if you have a function, how do you find its inverse? And there's two ways of doing that. First, I want you to be able to use the graph of a function in order to create the graph of its inverse. All right, so that's finding an inverse in a graphical format. And then the second thing I want you to be able to do is to find the inverse of a function algebraically, meaning if you're given the equation of a function, you'll use algebraic methods in order to be able to find out what the equation of the inverse of that function is. So those are our goals. Let's see how this is done. Now where we want to start is by talking about what the inverse of a function is. In math, whenever we're talking about inverses, we're talking about things that undo one another. And the same is true whenever we're talking about inverses of functions. Let's suppose that you've got a function f that maps this value a to b. Remember, with functions you always have inputs, outputs. Let's say there's some function f, all right, and it's such that when you plug a into function f, the output that you get is b. Okay, well, the idea of inverses I said a moment ago in a mathematical context is they undo one another. So, if function f maps a to b, what's going to happen is that the inverse of function f, written this way, all right, looks like f to the negative first power, but the way you're going to read this is f inverse. The inverse of f would take that value b and as an input, and it would give you a as an output. So f inverse of b would equal a. All right, so an inverse undoes what the original function did. This mapped a to b, and then the inverse gets it back. Another way of saying that is if you were to make a composition out of a function and its inverse, all right, or in other words, if you wanted to find f inverse following f of a, here's how that's going to happen. This would tell me to plug a into function f, and if I plug a into function f, it would give me b. And then it would tell me to take f of a, which is b, and plug it back into f inverse. And whenever I do that, it's going to give me back to a. So whenever you make a composition out of a function as inverse, you get right back to the original input value that you started with. F inverse following f of a is always equal to a. All right, inverses undo one another. That's the main idea with this conversation here. And one more thing to make note of before we go on to an example of finding inverses. Essentially, the way that you find out what the inverse of a function is this. All right, so you see that's x and that's y if we're talking about this being the domain of the function and this being the range. To create or to find the inverse of a function, what you really do is you switch the domain and range values. You interchange the domain and range values, or you interchange the x and y values. All right, or another way of saying it is that whatever the domain of the function is, that is the range for the inverse, because this was input for the domain, but this was the output for the inverse. And whatever the range for the original function is, or whatever its output for the original function is, becomes the input for the inverse, or the domain of the inverse. Switch domain and range, switch x and y values. That's how you find an inverse. Now let's do that with a specific example. All right, the directions here say that we're going to sketch the graph of a function f that is defined as being equal to x squared minus 1, and then we're going to sketch the graph of its inverse. Now, I'm going to use the aid of a table of values in order to create the graph of f. And I've taken the liberty of going ahead and making up some input values and output values that belong to one another. For instance, if you input negative 2 into this function, you would square that and get 4, then 4 minus 1 is 3. And you can check my other output values if you would like to. And what I'd like to do right now real quickly is just go ahead and plot each of these input and output values and sketch the graph of this quadratic function, which I hope you know is going to give us a parabola. So there's a graph of f of x right there. Now remember a moment ago I was telling you that the way you can find the inverse of a function is so you simply interchange the x and y values. Now that's what I'm going to do, but I'll try to explain it in more detail. If in the function f, negative 2, the input negative 2 gets an output of 3, that would mean that the inverse of f would take the number 3 and it would map it back to negative 2. And similarly, if f maps -1 to 0, the f inverse would map 0 back to -1. Essentially, I'm just switching the x and y values here, and I'll end up getting the coordinates that I need in order to graph or sketch the graph of f inverse. Like so. Now let me go ahead and plot those points and sketch the graph. And you see there's the graph of the inverse right there, just created again by switching the x's and y's with one another from the original function. Now one last thing I'd like to show you on this slide is a cool relationship between the graph of a function and a graph of its inverse. I'm going to graph a line on the screen, and it's going to be a line that you ought to be familiar with, the line y equals x. One of the things that is cool about the graph of a function and its inverse is that they were reflections of one another. And the line of reflection that you can reflect the function in to get the inverse is simply this line y equals x. All right, if I were to reflect this graph here, for instance, the point -2, 3 would get mapped over to 3, -2. Can you see how those are reflections of one another in the line? And then you can see, for instance, that the point 2, +3 gets reflected to 3, 2. Whenever you just switch x and y values like that, you always reflect in this line y equals x. And so on your graphing calculator, for instance, if you ever want to know if you actually have the correct inverse of a function, you can graph them both and then graph the line y equals x and really see, is this function a mirror image of its inverse in the line y equals x. All right, really cool. Let's look at algebraic ways of determining the inverse of a function now. All right, the directions here are telling you to use a variable interchange, which I'll explain momentarily, in order to find the inverse of that same function that we used a moment ago, right? F of x equals x squared minus 1. We just graphed that and its inverse a moment ago. And then we're going to state the domain and range of the function and its inverse. Okay. So this you've done in an algebra class before, Algebra 2, and I'm just going to remind you of the method. If you want to take the equation of a function and find its inverse, what you're going to do first of all is not use function notation. You'll rewrite it instead of using an f of x with a y. So our equation is y equals x squared minus 1. And then we'll use that same idea we did with the graphs where we switch the x values and y values with one another. And we will literally switch the x's and y's within the equation with one another. All right, and so that would mean when I switch the x and y's, that equation, instead of y equals x squared minus 1, would become x is equal to y squared minus 1. All right, so you interchange the x and y values with one another. And then what you do is you try to rewrite it so that y is by itself in that equation. So we're going to solve that equation for y, which is going to be a couple of step process here. We can add 1 to both sides and get x plus 1 is equal to y squared. And then we can take the positive and negative square root of both sides, because remember there's a positive and a negative number that you can square always, unless you plug in 0 here. That will give you the same thing. All right, and we want to be able to find both those things. So we could, I'm going to write this on the left, we could say that y would equal the positive or the negative square root of whatever x plus 1 is. All right, and then if I want to rewrite that back using function notation, which is sometimes appropriate with inverses, is not always, then we could say f inverse of x is equal to plus or minus the square root of x plus 1. All right, now we can go back here in a moment, but you've got the graphs on your paper. That sideways parabola that we had on the last slide, this was its equation. The equation would give you that same thing. Okay. Now I also said state the domain and range of the function and its inverse. I'm going to do this in a table format. And in that table, I'm simply going to make a column for the function and for its inverse, and then state the domain of each, and I'll state the range of each. I'll actually start with the domain and range of the original function. All right, which I can get a couple different ways. If you've got the graph of the function in front of you, as you should since you're taking those notes, then that's a good place to look and get the domain of f and the range of f. But let's just look at the equation right here. If we're trying to think about what the domain is for this quadratic function, we have to think about, are there any restrictions on what values I can plug in onto the function? And there's no restrictions on the numbers that you can square. And so indeed, we could say that the domain of this function is that x could be any real number. X would just be an element of the reals. It could be anything from negative infinity to positive infinity if you're using interval notation. All right, now in terms of the output values of this function, which again you'll see this easily on the graph, if you're squaring a number, it's guaranteed that you're going to get a non-negative value. We only work with positive numbers in IB, remember? Sorry, real numbers as opposed to imaginary numbers. And so squaring any real number is going to give you a non-zero, is going to give you a value that's non-negative. That's what I'm trying to say. Now, that means 0 is the smallest possible output you can get from just squaring. And if I'm then subtracting 1 from all of my outputs, that means the smallest output I can get from this entire function is -1. So I could say that the range is that y has to be greater than or equal to -1. If you look at the graph, the vertex of the graph, its y coordinate was -1 and the graph opened upward, so you can kind of see that. All right. Now I'm stating the domain and range of the function in its inverse just to reemphasize that whenever you create a function, or an inverse from its function, all you do is you switch the x's and y's, and another way of switching the x's and y's is to say that you're switching the domain and range. And that means that whatever the domain was for the function, that's going to become the range for the inverse, right? Because the inverse just takes whatever your output is from the function and spits it right back to the same thing that you started with. And so if the domain of the function was all real numbers, then that means the range of the inverse would be all real numbers. Now, the only thing that I'm not going to keep the same is I'm not going to use y whenever I'm talking about range, and I am talking about range here. So I'm not going to use x when I'm talking about range, I'm going to change it to a y. So we could say that the range of the inverse would be that y has to be a real number. Then the range of the inverse, of the function becomes the domain of its inverse. And so if the output values or the range for the original function were all values that were at least -1, well, that means that the input values for the inverse will match that same criterion. It would be x is greater than or equal to -1. All right, functions and inverses undo one another, and to find the inverse of a function, you just interchange x and y values. Whether you're doing that with an equation or whether you're doing it with a graph, it's always going to work. All right, guys, thanks for watching. I'll see you next time.